Hello and welcome to lesson 6 in the series on classical mechanics. This lesson is going to be on Poisson brackets. And as always, the booklet to fill in is in the description. Now, the key point of Poisson brackets is that when you do quantum mechanics, these are what become the commutator. But additionally, if you want to do very mathematical physics, the Poisson brackets give a nice algebraic structure, which in maths is called a Lie algebra. So if you ever go down that path, you'll be able to use all the theorems and techniques from Lie algebras, and they relate to Poisson brackets. So what is the definition of a Poisson bracket? So if we have any two functions of the coordinates and the generalized momenta, then the Poisson bracket of f and g is given on screen. Note that lots of resources, or lots of books, define this the other way around. So it would be df by dp, dg by dq. Take away dg by dp, df by dq. And the only difference here is an overall minus sign. So you might find from other books and other resources that there's a minus sign in everything. But that's just because they define this the other way around. We're now going to look at some examples for Poisson brackets. So before we can calculate the Poisson brackets, we're firstly going to need to calculate all the partial derivatives. So we start off with df by dq, and that's 2q, df by dp, and that's 0, dg by dq is 0, and dg by dp is 2p. We now have the definition of the Poisson bracket, and because there's only one q and one p, we don't have the sum over all the different coordinates, since there's only one. And then we substitute in for all of these partial derivatives, and we get 4qp. The next example you can do on your own, and then come back to the video for the solutions. Okay, now you've had a go. Firstly, the individual partial derivatives are given by this. And then we substitute this into the definition of the Poisson bracket, and we get the following. Okay, for the next example, I'll do the first part, and then you can have a go at the next two parts on your own. And you may think that these look very similar, because they are very similar to the canonical commutation relations in quantum mechanics. So for the first one, we substitute in for the definition of the Poisson bracket, and we're keeping the sum over I since I haven't said anything about the system we've got or how many different coordinates there are. And in this case, dqa by dqi is just the Kronecker delta. So if qa equals qi, then this is just 1. If they're different coordinates, then it's 0. And dq by dp are always 0, no matter what the subscripts are. So here's after we calculate the derivatives, and then the final result is just 0. Okay, now have a go at the next two, and then I'll put the solutions up on the screen. Okay, for the next one, we have the definition of the Poisson bracket. Things are 0 and the Kronecker delta in the same kind of way, and then that gets us 0. And then finally, for q and p, the first term in the sum is just 2 Kronecker deltas, and the last term is 0. We calculate the sum, we get delta AB. So the Poisson bracket has some nice properties. The proof for all of these properties are in the booklet. So after each property or at the end of the slide, you can go through the algebra in the booklet to see where they all come from. But I'm just going to go through and say what the properties are. So firstly, we've got anti-symmetry. So if we swap the two functions, we get a minus sign. Then we have linearity. So if the first argument is alpha f plus beta g, where alpha and beta are just ordinary numbers, we can split this into two Poisson brackets, and we can just pull the constants out the front. Secondly, or thirdly, we have the Leibniz rule. And the Leibniz rule is kind of like the product rule from calculus, where in the product rule, if you want to act on the multiplication of two functions, you do it to one and then do it to the other and you add those together. So it's the same kind of rule. And finally, we have the Jacobi identity. And this is if we cyclically permute all three functions in this Poisson bracket in a Poisson bracket, and we add all those together, we get 0. And do note the order. The letters are moving to the left and cycling around. And because of the first property, the anti-symmetry, all of these properties also hold for the other argument. So the second argument in the Poisson bracket is linear. The Leibniz rule applies to the second argument, and there's a Jacobi identity for the first argument. So both of these, also all of these properties hold for both arguments. We can use the Poisson bracket to work out how any quantity evolves in time. So the time derivative of any function, f, is the Poisson bracket of f with the Hamiltonian plus the partial derivative of f with respect to t. Now normally, f is just a function of q and p, and it isn't explicitly a function of time. So normally, this last term is 0, because there's no explicit time dependence of f. And now this equation means we can find an equation of motion for anything. So rather than just having the equations of motion for q and p, we can find an equation of motion for any function of q and p. And again, the algebra for this is in the booklet, so go through it and you'll be able to see where this comes from. The next example is the Hamiltonian for a pendulum. Have a go on your own and then come back to the video and I'll put up the solutions. Okay, now you've had a go. Firstly, we calculate the individual partial derivatives. Then for part A, we use the definition of the Poisson bracket and simplify. And then for part B, we do the same thing. We can also use Poisson brackets to calculate conserved quantities, or to work out if a quantity is conserved. So if we have a function, and we assume that it doesn't depend explicitly on time, that is, this f is just a function of q and p, then f being a conserved quantity is equivalent to the Poisson bracket of f and the Hamiltonian being 0. Okay, for the next example, we want to show that for a Hamiltonian in a central field in 3D, that angular momentum is a conserved quantity. And so what we want to do is we want to compute the Poisson bracket between Lz and h. I mean, we're only doing this for Lz, but it would work exactly the same way for any of the other components of angular momentum. So firstly, we're going to calculate the individual partial derivatives. So we have dh by dx and dh by dpx. And then the same kind of thing would be for y and z, where x is replaced by y and z. And then we also need to calculate the partial derivatives of Lz. So dLz by dx is py, dLz by dy is minus px, and dLz by dz is 0. Then similarly, with momentum, dLz by dpx is minus y, dLz by dpy is x, and dLz by dpz is 0. And now we want to actually calculate the Poisson bracket. So here is the Poisson bracket between Lz and h, where I've expanded the sum for each of the three coordinates x, y, and z. And then we substitute everything in, and then we see these two terms cancel, and these two terms cancel, and so we get 0, which means this is a conserved quantity. The next example is for a diatomic molecule, and you need to show that the total momentum P is conserved. So have a go on your own and then come back to the video. So firstly, here are all the different partial derivatives. Then we have the definition of the Poisson bracket, and we substitute all of those in, and we see that everything cancels and we get 0. So it is a conserved quantity. The final thing we're going to look at is Poisson's theorem, and this gets us... The final thing we're going to look at is Poisson's theorem, and this is a way to use two conserved quantities to find a third. So if we have two conserved quantities, then the Poisson bracket of those conserved quantities is again a conserved quantity, and the algebra for this is in the booklet. However, note that often the final result is not that interesting. It's either 0 or a combination of f and g, although that's not always the case. For things like angular momentum, you do get a new conserved quantity. So, in summary, we defined this quantity called the Poisson bracket, and then we saw that we could use this to calculate an equation of motion for any quantity f. So the time derivative of f is the Poisson bracket plus the partial derivative with respect to time. And often this last term is just 0, so f doesn't have any explicit time dependence. And then finally, we saw that f is a conserved quantity if the Poisson bracket with the Hamiltonian is 0.